Let's think back to rectangular coordinates. What did we learn after we learned how to plot points? We learned how to plot many points that formed a pattern. And then we learned that there's equations using the variables x and y that allowed us to draw graphs of all these points. Well, we know how to graph points in polar, so I guess the next step would be to graph some equations. And you can see in polar, we can actually create really cool looking graphs. But we'll have to start out basic and then build up to that. So let's start with a really simple equation. How about the equation r equals 3? Pretty simple equation. It doesn't even have a theta involved in it. So let's backtrack for a second. Back in rectangular, let's say we had y equals 2x minus 1. What did we do? We made a t-table with x and y, and then we picked a value for x, and we plugged it in, and we got the corresponding value for y. And then we picked another value for x and figured out what y was, and so on and so on and so on. And then we plotted those points, and then we learned after a while that, oh, this gives us the equation of a line. And then we didn't have to make our t-tables anymore, and we use this information here to help us draw the line. Okay, so now we're going to do the same idea with that in polar, except now we don't have a theta in our equation. We just have an r. So that's going to change how we fill out our table a little bit. It'll actually be a lot easier. And so in our table, we know r has to be 3, no matter what we do. So all the r values have to be 3. Theta can be anything we want because it's not defined in our equation. So I don't know, theta could be 0, or it could be pi over 6 if we're in radians, or it could be pi over 4, or maybe pi over 3, or pi over 2, or 2 pi over 3, maybe pi. Let's go even faster. How about 3 pi over 2? Hey, how about 2 pi? Okay, let's plot those points. So when theta is 0, r is 3. Where's that? That's right here, isn't it? At pi over 6, r is also 3. There's pi over 6, and that's r equal 3. At pi over 4, it's 3. Wait a minute, I'm starting to see what's going on here. At pi over 3, or 60 degrees, r is 3. At pi over 2, it's 3. At 2 pi over 3, at pi. At 3 pi over 2, oh, I know what's happening. I'm just getting a circle of radius 3. Well, that makes sense. So theta can be any angle at all. And we could go past 2 pi, but we'd still be back on the same circle. So r equals 3 gives me a circle centered at the pole of radius 3. Well, that makes sense. So from now on, I guess I wouldn't even need to draw a t-table for that. I could just plot it. R equals any constant is a circle centered at the pole of radius equal to that constant. All right, let's try another equation. How about, this one is theta equals 5 pi over 6. Notice there's no r value defined here. So r can be anything I want, but theta has to be 5 pi over 6. So I'm going to fill out theta, 5 pi over 6. R could be 0. Well, that's an interesting point. Where's 5 pi over 6? Let's see. 5 pi over 6 is right here, isn't it? Okay, and theta or r equals 0 would just be at the pole. Let's pick another one. How about, theta has to be 5 pi over 6. How about if r is 1? Well, I could graph that. Would be this point right here. Okay. How about, theta has to be 5 pi over 6. How about r is 2? Oh, wait a minute. I'm starting to see what's going on here. Theta equals 5 pi over 6. R equals 3. And then r equals 4. Let's be creative. How about r equals negative 1? Or r equals negative 3? Oh, how about r equals 2.5? But theta has to be 5 pi over 6 for all of these r values. Now, what happens when you start plotting more and more and more of these? You see the pattern that's going on. So we had 1, 2, r equals 3, r equals 4, r equals 2.5. Negative 1 would go in the opposite direction. Negative 3 would be here. negative 3.5, negative 4.25. Oh my gosh, I think this is just giving me a straight line that goes through the pole at that 5 pi over 6 angle. Oh. So now we know that if we get an equation in polar that's theta equals a constant, it's just going to be a line that goes through the pole at that angle in both directions. The negative r helps me go in that direction. Well, that makes sense. Okay, let's try another one that's a little more interesting. Let's do r is equal to theta over pi. Oh, now this one has r and theta, so now I'm going to have to work a little harder in my table here to come up with values. But before I do that, I want to point out something again. In rectangular, we usually did equations like this. And then, what did we do? We picked a value for x, and then we plugged it in to figure out what y equals. So that would be, what, 5? Okay, and then we pick another x, 7. And what do we get? 13, etc. And our coordinates are x comma y in rectangular. In polar, it's r comma theta. But a lot of times in polar, we write our equations not as theta equals in terms of r, like here, y in terms of x. We do it r in terms of theta. So usually here, we always picked an x and then plugged it in to figure out y. Here, we're going to pick a theta, plug it in, and then figure out what r equals. So it's easier to pick angles first and then evaluate the r value. So just wanted to point that out because it's a little backwards from what you've been doing for a long time. So I didn't want that to get confusing. Okay, also notice we have a restriction here. The thetas that we pick have to be between 0 and 4 pi. So let's try and go in order. I think that'll make life easier. So let's start with 0 radians. And then we'll pick, well, let's just plug that in. So I plug in 0 and I get r equals 0 over pi, which is 0. Oh, so that's just a point that's at the pole. So I'll plot that right there at the center. Okay, let's pick another angle. How about pi over 6? So r is going to equal theta. Oh wait, so I'm plugging in pi over 6 for theta, and then I'm dividing it by pi. How do I do that? Wait a minute. Let me write it over here. Pi over 6 divided by pi. I could make that pi over 1. And now I have a complex fraction, and I know dividing by a fraction is the same as multiplying by its reciprocal. Ooh, and the pi's cancel out, and I get 1 over 6. So when theta is pi over 6, r equals 1/6. Now, that's going to be a little tough to graph. Here's pi over 6. 1/6 of a unit out, boy, I can barely even mark that on there. Unless I change my scale, of course. All right, let's try another one. How about we do pi over 4? Well, then what am I going to get for r? I'm going to get r equals pi over 4 over pi. Well, that's going to give me 1/4. I'm still going to have trouble trying to graph that one. Pi over 4, 1/4, I don't know, somewhere about there. So maybe I need to pick some angles that are a little bigger so I can actually have points on my graph. So let's do pi over 2. Then what are we going to get? You're going to get r equals 1/2. That's a little easier to graph, so at pi over 2 I'm at 1/2. Notice my r's are getting bigger as my angles are getting bigger. How about 3 pi over 4? Then r is going to equal, so notice I'm plugging the angle in here, dividing by pi to get r. So I'm taking 3 pi over 4 in there, divided by pi equals r. So 3 pi over 4 divided by, and if it helps to write it out on the side, I wrote the first few out, then do that. Have some scratch paper or somewhere over on the side where you've got some room. Work out the equation and make sure you're not making a mistake, because if you mess up one, then I think you're going to be in trouble. So you should get r equals 3/4. So I'm going to plot that point. 3/4 is probably, I'm guessing about here, looks good. Okay. How about we go to pi? Oh, well, pi divided by pi is 1. Finally. I get an integer answer. I can graph that one. Okay, let's start jumping a little further. How about I go 3 pi over 2, divide that by pi, and I get 3 halves. How about 2 pi? Divided by pi gives me 2. How about 5 pi over 2? Then I'm going to get 5 halves, or 2 and a half. How about 3 pi? Divided by pi gives me 3. How about 4 pi? Divided by pi gives me 4. Okay, so let me plot those. So at pi, I was at 1. So at 3 pi over 2, I'm at 1 and a half. At 2 pi, which is back to 0, r is equal to 2. At 5 pi over 2, I'm at 2 and a half. At 3 pi, I have r equals 3. If I did 7 pi over 2, I'd get 3 and a half. That would be here. And then at 4 pi, 2, 3, I'm at 4. Notice the r values here, as theta gets bigger, that's why I did them in order. I just didn't want to jump all over the place. So starting at 0 and doing them in order, paying attention to any restrictions, and then I look at the pattern, my r's are getting bigger and bigger, slowly, but they're always getting bigger. So now I'm ready to go ahead and connect these. And so I'm going to connect these with a smooth curve in the order that I was graphing them. And so you can see that what's happening here, you are getting very sleepy. Boom, and I got to stop at 4 pi. So, and if I didn't have to stop, if there were no restrictions here at all, no restrictions at all, then it would just keep going, and it would just keep getting bigger and bigger and bigger. This was actually discovered a long time ago by a mathematician, Greek mathematician named Archimedes, and so this is called the spiral of Archimedes. So you can see with a really simple equation in polar, we get some pretty cool graphs. So we're going to focus on a few specific types of graphs, but for now, you know that r equals a constant gives us a circle centered at the pole with that radius, and theta equals a constant gives us a straight line going through that angle and also going through the pole. And now we learned that we get spirals when we do r equals theta divided by a constant. And if it's pi, it's really easy to calculate all the values in our table. If there was a different constant, we'd still get a spiral, but it'd be a lot harder to make our table of values. Okay, so that's the beginning of graphing. We'll do some more graphs later on. But now that we know how to draw graphs of equations, maybe we should talk about converting equations between polar and rectangular. Just like once we learned how to graph points, plot points in polar, then we converted those points back and forth. So now I want to convert points. So as a review, when we take our two systems and combine them, we can relate our variables, and we had these 4 equations that helped us convert from either rectangular to polar or polar to rectangular. So now let's use those equations and let's try and convert. So I've got my handy arrow over here, and then I've also, let's see, I need a copy of those equations somewhere. There they are. All right, so I have an equation that's in polar. I have an r and a theta. I don't want any r's and thetas. I want to change these so I just have x's and y's. So how am I going to do that? Well, right now I don't see any direct conversions here. I don't have an r equals that I could convert. I have an r squared. I don't even have a cosecant anywhere. So maybe let me go back to this equation and can I manipulate this somehow? What was cosecant? Oh, wait a minute. Isn't cosecant 1 over the sine? So how about I change this to 3 over sine? Now, that still doesn't seem to help me. If I had r times sine, then I could convert it to y, but I just have a sine. Well, but algebraically, I know that I could manipulate this equation. If I multiply both sides by sine, then I'd be in business. Because I'd have r times the sine of theta, doesn't matter which order I write that, multiplication is commutative, equals 3. And now I say, wait, r sine theta is the same as y. So I can rewrite that as y equals 3. And now I've converted. I had an equation in polar, now it's in rectangular. This had r's and thetas, no more r's and thetas, and it just has a y equals. Doesn't have an x, but that's okay. Sometimes it has both x's and y's. Sometimes it just has one or the other. All right, let's try another one. Or maybe hit pause and, oops, let me get my arrow back. All right, so maybe hit pause and try this and then see how you did. All right, so let me take my equations here. Oops. Drag these down, because I'll use them again. Theta equals 5 pi over 6. So how am I going to convert this? Theta. I don't have a theta. I have a tangent of theta, and then I could convert that. So, well, how about I take the tangent of both sides? So how about I write the tangent of theta? Now I can convert that. And then I have the tangent of 5 pi over 6. We learned that from the unit circle. We could figure that out. So tangent of theta, I'm going to replace that with y over x. So that's y over x. And equals the tangent of 5 pi over 6. Wait a minute, I'll do some side work here. 5 pi over 6 was over here on the unit circle. The tangent is sine over cosine. The sine was 1/2. The cosine was negative root 3 over 2. The 2's cancel. I get negative 1 over root 3. Then we usually had to rationalize that. So I got negative root 3 over 3. Oh. So the tangent of 5 pi over 6 is negative root 3 over 3. So I have converted this equation in polar, now is in rectangular. I don't have any r's and thetas. I have a y and an x. The last step, and like I said, this is correct. We've converted it. But usually we like to try and see if we can write it as y equals. So what if I multiply both sides by x? I get y equal negative root 3 over 3 times x. And there we have it. And now you should recognize that, that's just a line with a slope of negative root 3 over 3 going through the origin. And as we learned earlier when we graphed this, that gave us a line that went through the pole. And that's the slope of the line. Interesting. All right, let's try one more. Once again, hit pause, try and convert it, and then let's see how you did. All right, so how did it go? Let me move this down here. Don't want to lose my arrow, take that with me. So how are we going to get rid of the r? Well, we look over here. If we had r squared, we could have replaced it with x squared plus y squared. Well, let's see, how could I get an r squared? I could multiply both sides by r. Yeah, that would work. Then I'd have r squared equals 4r. And then the r squared would be x squared plus y squared. Oh, but wait, now I have an r on the other side, and I'm still where I was at the beginning. So maybe that's not the best way to go. How else could, what if I squared both sides? That's another way to get r squared. So I'm thinking of things that I've learned in the past and how to manipulate equations algebraically in order to wind up getting something useful from these conversion equations. So the r squared, I can replace that with x squared plus y squared. So I have x squared plus y squared, and 4 to the second power is 16. And you should remember from geometry that that's the equation of a circle centered at 0, 0 with a radius of 4. And what we just learned earlier in our graphing, r equals 4, gave us that same circle. Okay, so these were polar equations and we converted them to rectangular form. What about the other way? Let's try and do that. Let's try and convert a rectangular equation and put it into polar form. So that means we have to get rid of our x's and our y's, and we need to get r's and or thetas. So let's see, what can I do with this? I have a 3x. Well, x is our cosine theta. So let me replace the x with r cosine theta. And then the y I could replace with r sine theta. And let's see what we got. That would give us 3 times r times cosine of theta minus 2 times r times sine of theta equals 7. And so we're done. We've converted it. Now, just like we did with rectangular, if you can, we'd like to take our final answer and write it in the form r equals. So let's see, maybe I can do that here. I could factor in r out of both terms on the left side here. So I get r times the quantity 3 cosine theta minus 2 sine theta equals 7. And then I could divide the quantity 3 cosine minus 2 sine from both sides, and I'd be left with r equals 7 over 3 cosine theta minus 2 sine theta. Now, this is not a form that you recognize because we really haven't done much graphing yet. But after a while, there should be some forms that you'll recognize when you look at the polar equation and you relate it back to the rectangular equation. Everybody looks at this and says, oh, I know what that is. That's a line. And it wouldn't take you too long to figure out the slope of the line and the y-intercept. And then you could graph it. Well, we want to get to that same stage when we're doing polar equations. All right, let's try another one. Convert to polar form. So let's keep my arrow, let's keep my equations. X equals -3. What are we going to do for this? Well, let's just take the x and replace it with r cosine theta. R cosine theta equals -3. Now we've gotten rid of, it doesn't have any x's or y's, and it has just r's and thetas. Now if I can, I'd like to solve for r though. So r equals -3 divided by cosine of theta. So that would be good. Or, if you'd like, isn't that the same as -3 times secant of theta? Because cosine is 1 over secant. And there's your answer. So you know what x equals -3 looks like if you graph that. Vertical line going through the x-axis at -3. Well, now you know that r equals -3 secant theta gives you that same line. Now, sometimes it gets really challenging when you have some rectangular equations to convert them to all polar, and even harder to try and solve for r. So I won't do this one, but I'll leave it to you if you want some more practice. A little hint, rearranging would be helpful. Maybe move the x squared and y squared together. That would be easy to convert. And then you can replace the x. And then you could replace that y. I think trying to solve that for r would be a lot more challenging, but I'll leave it up to you if you want some more practice. So now you should have the basic idea of how to graph a polar equation by making a t-table, plotting some points, and also how to convert equations from rectangular to polar and from polar to rectangular.